Okay, so I should start by saying I'll make a slight modification to the title. And so what I want to, I think we can start about here, is that okay? Okay, so the title is going to be Stochastic Dynamics of Interacting Particle Systems. So the reason I make this change is because I want to stress that it's the dynamical aspect that we'll be studying. And basically we're studying stochastic dynamics of classical particles, and I want to show you some interesting phase transitions that can occur through many-body interacting particle systems. So the key difference in this week to what you saw last week is that I attended some of the lectures, and most of the lectures you start with some partition function. That's your starting point, and then you calculate. Here, no partition function. We have to take a step backwards, and we just start from dynamics. And from the dynamics, we try and work out what happens. So that's the key difference. No partition function, you start from dynamics. So this is lecture 1. And in lecture 1, I'll outline the elements of what I mean by stochastic dynamics and the framework that I will use. And the framework that I will use is basically Markovian dynamics with transition rates. So I'll try and explain exactly what I mean by that. So this is an introduction to stochastic dynamics. And firstly, I'd like to come back to this point of the difference between an equilibrium system, where we can write down a partition function, and a non-equilibrium system, which is generally what I'll be talking about. So this is part 1A. So it's equilibrium versus non-equilibrium. So let's just recap what we understand from undergraduate physics by an equilibrium system. So if you remember, for equilibrium, we can think of our system, and so this is the system. And it lives in a heat bath, usually, or we think of it as in some environment. And the environment has temperature T. So this is the environment. And then there's some passive exchange of energy with the environment. So energy just gets exchanged back and forth until we get to what we call thermal equilibrium. So you learned that this was given by the Boltzmann distribution. We said that the probability of some configuration C of the system. So here I use C to indicate a configuration. Or sometimes this is, at undergraduate level, you refer to it as microstate. So the detailed description of the system. So this equilibrium probability, when the system, after a long time the system has reached equilibrium, is just given by a Boltzmann weight. So we have some energy for each configuration over the partition function. And the partition function is the sum over all the configurations of all the Boltzmann weights. And that's where that was, as I mentioned, usually the starting point in equilibrium is the partition function. And from that, you can calculate whatever you want. So let me just generalize slightly. We can also have equilibrium with respect, so I should have said here, the system, we have a passive exchange of energy with environment. Also, we can have an exchange of particles if we want to generalize to Gibbs-Boltzmann distribution. So you will have seen this as well. So then exchange of particles, we have instead of temperature, we have something called chemical potential. And then this is N, where N is the number of particles. And we usually write it like that. Suddenly I'm concerned. I don't think there's a beta there. Sorry, this is not important. But anyway, so that's if we want to generalize to exchanging particles with the environment. Okay, so hang on, let me just do my shoelace up. So that's equilibrium. So non-equilibrium is when that doesn't hold. And there's basically two ways this doesn't hold. The first was the assumption that we reach equilibrium after some long time. So we reach after a long time, the system settles into a stationary state. So it may be that we haven't got yet to the stationary state. We're waiting to get there. So we can be non-equilibrium. Firstly, we can still be relaxing to equilibrium. And it may be that the relaxation takes a very long time. So for example, in glasses, basically the system gets, we cool something, the system gets stuck out of equilibrium in some sort of liquid configuration, it just gets frozen there, and it can never get to the true solid-like equilibrium state. It's always stuck in liquid-like configurations. So that's what a glass is. It never actually gets to equilibrium. It very, very slowly evolves. Also, we can have phase ordering dynamics where we want to get to the equilibrium state, let's say an ordered state, and the ordering process is quite slow due to some conserved quantities. So that could be of interest, the relaxation to equilibrium. So the examples I mentioned there are glasses, very, very slow relaxation, or phase ordering dynamics. Or it may be, the other thing that can happen is that we reach some stationary state after a long time, but it doesn't obey the conditions that we've set for equilibrium, which is this passive exchange with the environment. It may be that somehow the system is driven in some way, and we'll give concrete examples of this. So the second way we can be out of equilibrium is if we reach some stationary state, but it's driven in some way. So it can, e.g., driven by the environment, so in which case we can, instead of this picture, we can think of the system, and then the environment drives a current of particles or energy through the system. So rather than being some passive exchange, the environment is pushing energy through the system. So we'll give some examples of that. Or it can be that the constituents are active in that they drive themselves, so that they move around by their own volition, rather than being some passive equilibrium with the environment. So we can have active constituents. So in this case, if it's a stationary state is driven in some way, we call it a non-equilibrium stationary state. So it's a little bit, it can be confusing at first. You can have a stationary state, but it can be out of equilibrium in this sense that it doesn't obey this condition for an equilibrium stationary state. So we call these, let's refer to them as non-equilibrium stationary states. And this is what I'll be mainly concerned with in these lectures, non-equilibrium stationary states. Or, if you think about it, we've got A and B. We could have C is both of the above. We could be relaxing slowly to a non-equilibrium stationary state, and so on and so forth. But in general, we can sort of unify these things at a very general level by saying that all these systems are defined by dynamics. Dynamics is the basic thing, rather than equilibrium properties such as energy and free energy. We're interested in dynamics. Okay. So that was the general introduction to say why we need to study dynamics. So now I want to lay out the framework of stochastic dynamics. First, can I check that, is my writing a good size? Yeah. How far back can you read it? Right at the back? Okay. Good. So the way we're going to do stochastic dynamics, we're going to assume Markovian dynamics. So Markovian simply means there's no memory of what happened in the past. It only matters what state you're in now. And we're going to use a description with transition rates. Important thing, transition rates, and sort of mathematically, from a technical viewpoint, you would say that we're considering Poisson processes. So what does it mean? Basically, in some small time interval dt, the probability of a transition from a configuration C to some new configuration C prime. So we're going from C to C prime in some small time interval dt. It's equal to our W. And the way I write it, you have to watch out for the convention. I'm going from C to C primed. And the reason is, as you'll see, is because I want to eventually write this W as a matrix. So I'm going from C to C primed, and there's a dt there. Okay? So that's in some small time interval dt. So the correction would be of order dt squared. So this is when we go divide by dt and take dt goes to 0. This becomes the transition rate. That's the important thing to remember. So W is the transition rate. And of course, transition rates are greater, well, possibly equal to 0 if nothing happens, if there's no transition. Greater to 0. And they could be large. You know, it could go to infinity, a transition rate. It doesn't have to be less than 1. So it's Markovian in that there's no dependence here on what happened in the past. It only matters on what configuration you're in right now, the system is in right now, which is C. It doesn't depend on history. And later on, I might mention some non-Markovian generalizations if I have time. But let's just stick with this for the moment. Also, right, so what I'm going to do now is to let P of CT, okay, this is obvious, this is just the probability that after time t, the system is in configuration C. So I'll abbreviate probability just to prob. There's a prob that at time t, system is in configuration C. Now, one thing you note here is that strictly, I need to say what the initial condition was. It's going to depend on the initial condition, but I've suppressed that, just otherwise it gets a bit long to write out. But remember, there's always an initial condition that we have to specify. Right, so the key equation is we want to write down an equation for how this probability evolves, because this is what we want to solve for, so we need an equation for it. So the basic equation is known as the master equation. And if you like, this is equivalent to the Schrodinger equation in quantum mechanics. It's your basic equation. So what I write down now is what's called the forward master equation. Because as we'll see a bit later, the next time there's also a backward one. But let's do the forward one for the moment. And it's easy just to write down quite intuitively. So I'll go up here with the forward master equation. So the rate of change of P is going to be two terms. The first term comes from probability going into configuration C. And we get that from, we sum over all the other configurations C primed. So strictly in here, there's a C prime not equal to C. And then I have the transition rates going from C primed to C. And then I have the probability of being at C primed at time t. Right, so that's the probability going into configuration C from the other guys, the other configuration. And then, of course, we have loss of probability from C. So again, we'll sum over C prime. Sorry, the intermediate is not equal to C. And we're going to all the other configurations from C. So I've got M. C prime, that's right. C. And we lose probability from configuration C. Yes, thank you, I made a mistake. I should be using W. I changed notation a little bit too soon. So this should be W. Okay, so that's the basic equation. So this is, as I said, this is the flux of probability into C. And this term gives the flux of probability out of C to all the other configurations. So that's a simple enough equation. We can tidy it up a little bit by putting all this together into one matrix equation. So I can write it as, now this is where I wanted to write M. So I can write it as the sum over C primed, and this time I'll include C in the sum. And I can write it as M of C primed, P, T with C prime. So then it's a simple matrix equation for the first derivative in time. And what is this M? So M, this is a matrix called Markov matrix. And it's basically when we're off diagonal, when C and C primed are not equal, it's just W. Then we put all this stuff into the diagonal of M. So minus delta C prime. Then this stuff becomes the sum. I have to write as the sum over C double primed. Okay. One moment. So I put the transition rate just one moment. No. Beg your pardon. Okay, that's correct now. So I've put all the transition rates out of configuration C into the diagonal of this matrix. So the CC element, the diagonal element, is the sum of the transition rates out of C. So then I put this just in one simple matrix equation. So this is omega by omega matrix. Is called the Markov matrix. And sometimes it's referred to as, in some texts, as the intensity matrix. But I think Markov matrix is more self-explanatory. And this omega is simply the number of configurations. So it's the size of the configuration space. So usually we have a large number of configurations, exponential in the system size, which is large. So this is actually, will be quite a large matrix. So then if we want to formalize things a little bit more, I can write this equation as, if I write it in a vector notation, so here I use Bra-Ket notation, or really Ket notation, but don't let this worry you. Don't get confused with quantum mechanics. I'm just using Ket to indicate a vector. So I'm just putting all my probabilities in a column vector and calling this column vector, denoting it by a Ket. And then I can just say that this is M times P of T. So because it's Markov, M doesn't depend on time. So this is a neat way of writing this, the master equation. Okay, so that's the one that you should be able to remember and write down. And that's what eventually we'll need to solve. So the first thing, we'll come back in a little moment to how would we solve this equation for all time. But the first thing is, as I mentioned earlier, we're interested in what happens after a long time. And that's what we call the stationary state. So the stationary state this occurs when t goes to infinity. Then we expect p to go to some time-independent distribution, which is the stationary state. And I'll denote this with an asterisk. So as t goes to infinity, it becomes time-independent, so the time derivative will be 0. So the equation we'll have to solve is 0. So all I've done there is to take this equation, set this derivative to 0, and then the p becomes time independent, and it's the p star. So I just want to solve this equation to give me the stationary state. So there's a number of ways of solving this. And now let's define what I'll call the equilibrium solution. you see here, we've got a sum of terms, and then minus a sum of other terms. And we have, for each C primed, we have one term. And the equilibrium solution is when there's a very simple cancellation of terms. So each C primed in this cancels with the same C primed in that. So that would be a simple way of solving this equation. And that's what we call the equilibrium case. The equilibrium solution is when W C primed, P star C primed equals W C primed C, P star C. And this condition is what we'll call detailed balance. Actually, one thing, I was intending to number the equations, and I forgot already. So let me go back and try and number the important equations. So this, the master equation, is equation number 1. Writing it in this form with the Markov matrix, let's call this number 2. Then using the ket notation, it's the same thing, but I just call it 2b. This condition for the stationary state, the condition for stationarity, I'll call 3. And detailed balance, this can be number 4. So I'm just labeling these equations. Okay, so why is this a significant solution? Well, I called these terms here the total flux of probability going into C. So each individual term is the individual current between configuration C primed and C. So what I see is that the current of probability going in to C from C primed is the same as the current going out. So if I could put on my sort of magic glasses and try and see probability flowing in my system between configurations, if I could sort of see into configuration space and watch the probability, then actually I would see no probability flowing. And I wouldn't know which way the probability was flowing, and then that has a lot of important consequences. So one thing then is, because I can't see any probability flowing, I could turn time backwards, and it would look exactly the same. And this has important consequences for various two-time correlation functions. So the equilibrium solution is very special, and there's a lot of important properties that go with it. But the general solution is not equilibrium. So just to summarize, what this means is that the probability current from here we're going from C prime to C is equal to the probability current from C to C prime, and that's why it's called detailed balance. At the microscopic level, there's no net flow of probability. So, for example, in the case of thermal equilibrium, we know that P star of C should be proportional, mentioned at the beginning, to the Boltzmann factor. So here I just consider thermal equilibrium rather than particle exchange. So let me just say it's e to the minus beta e c. Oh, by the way, one thing I, of course, forgot to say way back over here is that this beta here, just in case you've forgotten, is 1 over kT, so it's inverse temperature. So anyway, so for thermal equilibrium, we want our stationary state to have this form, and so then effectively, we can choose the transition rates to satisfy this. So, we know what our equilibrium is, so we can construct dynamics that will take us there. Essentially, that's the game. And just putting this in here, we see that our dynamics should obey this guy divided by W C prime C. Well, it should be P star of C divided by this. So e to the minus beta E of C minus E of C prime. And I'll call that e to the minus beta delta E. So delta E is the energy change when we go from C primed to C. So we know to have detail balance, that's what we want. And so there's a number of ways of choosing the rates to satisfy this. There's a few choices, and probably some of them you will have used various choices to do computer simulations of simulating dynamically an equilibrium state. So some choices are, let me just squeeze it here. So Glauber dynamics is when we choose W, C, C prime. So some overall constant rate I'll call gamma, and then 1 plus e to the minus beta delta E. And you can check that that works. So if I work out this, then I will get e to the minus beta delta E. Because it will be this divided by that over 1 plus e to the plus beta delta E. And if I work it out, then I do get this. So that's one choice, but there's other possible choices. What's known as metropolis is if we choose the transition rate to some constant rate gamma, if delta E is less than 0, so if the change in our system configuration decreases the energy, then we just give it some rate gamma. And if the change were to increase energy, then we give it a lower rate. And it's gamma e to the minus beta delta E, if delta E is greater than 0. So in that way, we sort of ensure that the transition rates are large when we're decreasing the energy. So it hopefully gets us to equilibrium more quickly. But these are just sort of simple examples to try and connect with some of you have been doing Monte Carlo simulations. Okay, so then I know I run out of board at some point over here. Can we agree about there? There's a point where I stop. So what I said is that this is an equilibrium solution, detail balance, and this is some way to obtain detail balance. Now, the opposite question is, given a set of transition rates, let's say, specified by the system, how do I know if those transition rates will generate a stationary state that satisfies detail balance? That's a sort of the converse question, which is not quite so obvious. If you're just given a bunch of transition rates, how do you know if you've got detail balance? And there is a criterion for this. So the converse question given our transition rate, when does so dB is detail balance hold? It turns out that a necessary and sufficient condition is what's known as the Kolmogorov criterion. So it's a simple enough condition, and it says if I take any sequence of states, that end up in the state I started with, then the transition rates, when I multiply them going one way round this loop, it must be the same as if I multiply the transition rates going the other way. So it seems a little bit strange, this, but it's actually very, very close to if you do electrostatics. And if you want a conservative field, then the path integral shouldn't depend on path. And if you go around in a circle, you should get 0. It's exactly the same idea. So the condition is that, okay, so if I start here, so if I start in state 1, I go to 2, and then from 2, I go to 3, and then so on until I get to state K, and I go back to 1. So I haven't written that very well. This is a transition rate going from 1 to 2 to 2 to 3, all the way up to K, and then back to 1. So that's going around the loop one way. It should be equal to going the other way, which is, if I go to write this backwards, 1, 2, so I start at 1, I go to K, and I go to K minus 1, and so on until I end up back at 1. So the product one way should be the product the other way. So that must hold for any sequence of configurations and I think I'm running out of space here, so I'll just leave the proof of that as an exercise so you can think about that in the tutorial. It's relatively straightforward to prove both necessary and sufficient conditions, and we can discuss that in the tutorial if you like. Right, so that was all. This discussion was the equilibrium case when we have detail balance. But when we don't have detail balance, then there will still be a solution to this that will give the P star, and that will be the non-equilibrium stationary state. When we have no detail balance, then we have our non-equilibrium stationary state. So again, I stress if we had put on our glasses and we could see probability flowing around in configuration space, in the non-equilibrium stationary state, although it's a stationary state, we would see probability flowing around. There'll be a circulation of probability in the configuration space, if you can imagine that. And so that's a key difference. So we need to think of, this is now the basic problem. How do we solve this? So let me say there are some simple cases where the solution is simple. So one simple case is if this sum over transition rates into some configuration C is equal to the sum of transition rates out of configuration C. So if you like, the total transition rate out of configuration C is the sum equal to the transition rates in. Then if you think about it, you can just put P a constant, and this equation will equal 0. So that's a very simple case where you end up with a constant probability. So each microscopic configuration is equally likely. But for that, you need this condition here. So if you have this condition, then it's a constant, and it'll just be equal to 1 over the number of configurations. But the general problem is that it's generally difficult. And we will look for cases where we can solve in a uniform way. So just, I have a couple of minutes. Let me just say, you might think, well, that's rather weak. This is just a linear equation, right? We know W's, we also know P's. It's a linear equation. Like, why can't we solve it? So yeah, in principle, you can put linear equations on the computer and solve. The problem here is that we want to look at systems that have a large number of configurations. Let's say exponential and n the system size. And we want the system size itself to be large. So it's exponential or something huge. So we want a huge number of configurations. So then you can't go to your computer, you can't solve, linear equations that have billions and billions of components. So you need to have some way in which the whole thing simplifies, and these will be some exactly solvable cases that I'll mention. So also you say, well, it's linear equations, surely there's a general formula. And in fact, there is a general formula for the solution. And I'm not going to present it because it's very deceiving. You can write down some complicated general formula, but it doesn't help you. In most cases, it gives you something so complicated it's no use. So although it's a simple linear equation, we need some special properties in which the equation simplifies somehow, and we can write the solution in some uniform way and allow us to look at larger and larger system size with the same solution structure. So that's why we need special exactly solvable cases. So yeah, please. Not necessarily. No. Right, the way I've defined equilibrium requires this condition. So you can have P star constant without having equilibrium. And we'll show some examples. We'll see some examples. I know it sounds a bit strange, but I'll show you some examples. Later. Not today, but later. Okay, so what I usually do, I have to clean the boards now. So we're halfway through, so I can clean the board, and we can just have a 2-minute break, and so you can chat, and we'll start again in 2 minutes. Okay? Okay, I saw that the other lecturers used yellow for the second half, so I'll try the same strategy. Also, I should say, I forgot to say at the beginning, please do ask questions if you have any questions and interrupt me. I'll be happy to have questions. So I didn't catch the beginning of your question. Yes. Yes, to some extent, that's what I'll be talking about to some extent. Certainly those two classes are nice and simple. Detail balance and all configurations equally likely are two simple classes. Right, more generally, there needs to be, in some very general levels, some sort of factorization in the configuration space. So, I mean, okay, that's saying something very general. You need some simplification where, let's wait until I give some examples. There will be some examples. Okay. No, the master equation, yeah, good question. Master equation is basically for when you have transition rates like this. If you have, you see, here we considered Markovian transition rates. You could consider something non-Markovian. And the simplest way is to think about that the transition rate depends on, let's say, the last time that a transition occurred. So it depends on some history. Then you can, but it's much more difficult to write down a master equation. You have to, it becomes much more complicated. Well, the other way is if you wrote Langevin dynamics, this can be Markovian. And it's not quite equivalent to Poisson process. But for this talk, yes, right, transition rates are always like Poisson process. So the Poisson process means that a bell rings with a certain frequency, and that's when you try and do transitions. So that's what I mean by Poisson process. So this is the transition rate. Sorry, I'm not being very clear. Maybe I can come back to these issues at some point later on if I have time. It's a good question, just I don't have time right now to get into the details. Okay. What I want to do now is to do some, okay, that was, the first half was some formalism. Let's now just do an example to keep our feet on the ground. So this is 1C. This is an illustrative example. So it's a one-dimensional random walk. So I have a lattice. So sites 1 up to L. So L is my system size. And I'll make it periodic boundary conditions that when it gets to L, if I go out this side, I come back here. So periodic boundary conditions. And my configuration C is now the position. I've just got a single random walker. And let's label it by J going from 1 to L. So here's a simple case. My configurations, I just simply have L of them. And the walker, so let's think of the random walker as a particle. And I want to think of it, so you may have met random walks when the time is discrete. Here I want to have a continuous time, but a discrete lattice. So the walker goes to the right with a rate P, say, and to the left with the rate q. So my transition rates are W going to the right would be J going to J plus 1 with rate P, and W of J going to J minus 1 equals Q. So they're my transition rates. And what you see, yeah, and I realized I didn't label the last equation when all configurations are equally likely. The condition for that, I should have labeled number 6. So if you can go back, that's when the sum over C prime W C prime C is equal to the sum over C prime W C C prime. And actually, this is certainly the case here. Because, okay, if I sum over the total rate out, if this is J, is P plus Q, and the sum of the rates in, I could have come from there with Q, and here with P, so it's also P plus Q. So I know the stationary state is that the particle will equally likely be anywhere, and that's what you would have guessed, right? So condition 6 holds. So P star J is actually just 1 over L. And the interesting thing is for P equals to Q. So this gives an example. Someone was asking about the difference between the detail balance and the equally likely state. So for P equals Q, actually you have detail balance. So everything's equally likely, and the probability of going from here to here is the same as going backwards, so you have detail balance. Whereas for P doesn't equal Q, you don't have detail balance, and then clearly for P not equal to Q, let's say P is bigger than Q, the particle will move around and around, and so you'll have some current. And so there'll be a current in the state, and that makes it a non-equilibrium stationary state. So we can also use that as a definition of a non-equilibrium state, when there's any kind of current flows in the stationary state. So the particle current here will actually be J equals P minus Q over L. So that's fine, that's the stationary state. Now let's consider the relaxation. So our forward master equation is d by dt P jt is P j minus 1 t plus q okay, so that's just the master equation. This term coming in from site, this is j, coming in from j minus 1 with rate p, coming in from j plus 1, going backwards, that's with rate q, and then there's rate p plus q of moving out of site j. So it's a simple equation. And here, okay, it's a linear equation in the probabilities. And the thing to note is that it's we've got periodic boundary conditions, and so it's homogeneous. So if we want to solve this equation, what method would you suggest? Oh, good, everyone's keen. Yeah, so that's the key thing. The homogeneous is the key thing. Then Fourier, some kind of Fourier transform will usually work if you have some homogeneous system, or translationally invariant. Now, the only thing I realized, I remember when I was a student, people would say, oh yeah, Fourier transform, and it'd be very confusing because everyone meant something slightly different, some particular kind of discrete or Fourier series, Fourier transform, and it all gets a bit confusing. So let me do it explicitly what I mean here. So here the Fourier transform, we're on a discrete lattice, so we need a discrete Fourier transform. So let's go through that in some detail. So let's write P tilde KT. So the tilde will mean the transform thing. I'll write it as, so that's a T in there. 1 over L, and then the sum over J over all the sites, 1 to L. And I'll write ZK to the power J, P, J, T. So ZK is just a shorthand, and it's for this plane wave thing. So e to the 2 pi I k over L. And I'm going to choose, so I should have L Fourier modes. And I'll choose just, you'll see why in a moment, I'll choose k to go from 0 to L minus 1. So I'm going to have L Fourier modes, but I label them 0 to L minus 1. How about orange? Is orange good? I can't see any more yellow chalk, so we'll try orange. Need some yellow. Okay. So what I do is I go back to this, oh right, sorry, this is equation number 7 now. So I sum this over J. I multiply by ZK to the power J, and I sum over J. So what I'm going to get right, that's just multiplying by zk to the j and summing, so that just becomes d by dt of my, oh right, dividing by 1 over L. So that's my transform. Then in here, I've got a j minus 1. So when you work this out, I've got zk to the j. I'm going to have to relabel the sum to get a j there. That's right. So when I relabel the sum, j goes to j plus 1, I'm going to get one extra factor of zk, because I'm going to have a j plus 1. So this is something that you need to work through yourself, but I'm going to have p zk from here, because the j minus 1. The j plus 1 will give me there'll be a q, and then it will be zk to the minus 1. When I relabel j goes to j minus 1, I pick up a zk to the minus 1. And then minus p plus q, p tilde k t. So that's the game. I've transformed, and I have a nice, simple differential equation that I can solve. So if I call all this stuff here, I just call it lambda k, then I see that p kt will just be e to the lambda kt times p tilde k 0. That's the solution. So great, that's the easy bit. Then, of course, the difficult bit with any transform is inverting the transform to get back to our, in this case, our real space, which is the probabilities. So let's go through the inversion slowly. So what I want to do is to invert this. And the orthogonality that I'm going to use to do that is the sum over k equals 0 up to L minus 1, zk, then this is to the power, let's say, j minus I, to some integer power. Then that, you can check it out. So if this power is 0, then clearly it's the sum of L terms that are 1. So it's L if j equals I. But if they're not equal, then actually the sum equals 0. And you can check that yourself by doing a geometric series. So it's 0 if j does not equal I, and I can write those two things as L delta ij. That's what I use for the inversion. So then generally, if my transform of something, like this is generally, if I transform something f of k, this is defined as 1 over L, sum over j equals 1 to L, z k. Let me write it as I this time. I equals 1 to L, z k to the I, f of I. So this is some function that's defined on real space. If I make the transform, then I can invert by noting that sum from k equals 0 to L minus 1, zk, and this time, thanks, this time minus j times f tilde k. Well, what have I got? I've got 1 over L, then I've got sum over k, let's be lazy here, sum over k, I won't write out all the sums, the limits of the sums rather. And then here I've got a sum over I, and I'm going to have zk to the I minus j fi. And then I know, because we just showed it, that this sum over k of this, it gives me a delta with an L, so I end up with sum over I, delta I j fi, and that of course is just, fi is f j. So that's how I invert this discrete Fourier transform. So doing that, I've got the Fourier transform here. So if I invert to get P of j, it will be sum k equals 0 to L minus 1, zk to the minus j, then this is simply e to the lambda kt p tilde k0. So the only thing left is to work out what p, the initial condition is. So if I take, oh, thank you. Please just put up there. So my initial condition, if I take p j t at t equals 0 to be delta j comma j naught. So that, what that's saying is simply that I start with probability 1 at j naught. I have some fixed initial condition. I could choose something more complicated like a distribution for my initial condition, but let's just say I start at site j naught. Then p tilde of k0 is simply 1 over L, and then it's going to be z k j naught. So putting that all together, I end up with p j t equals 1 over L, sum over k equals 0, L minus 1, e to the lambda k t. Then I'll write out these z's. I've got zk will be j naught minus j. So remember, zk was e to the 2 pi I k over L, and end up with j naught minus j. Okay, so that's equation 8. So that's a little bit of work, but I think it's worthwhile. working through that. Also, I'll try and give, if I have time, I'll try and give some exercise that gives you some practice with this discrete Fourier transform. That's just a slight generalization of what we've done here. Okay, so the important thing here are these plane waves are what we'll call the modes of the system. So we've got a sum over the modes. And then we've got, each one has this factor, lambda k. So if I go back to what lambda k is, these are actually what I'll call the eigenvalues of the modes. I'll try and say why more generally in a moment. So what we've done is that we have L eigenvalues. So E values is eigenvalues, lambda k, which is a P zk plus Q zk to the minus 1 minus P minus Q. Okay, and they come in front of each mode. So these eigenvalues, because our transition matrix is not necessarily symmetric. So our matrix M, well, okay, let me just say, we'll see in a moment more generally what's happening, but let's say that these are generally complex eigenvalues. But the interesting thing is that they're complex because, remember, zk is a complex number. But if p equals q, the sum of zk and z to the k minus 1 is just going to be cos. So if p equals q is a detailed balance case, then these eigenvalues become real. So again, you see that detailed balance is a special case. So lambda 0, which is, okay, so I should have written here zk equals e to the 2 pi I k over L. So then you see that the p equals q, zk plus zk to the minus 1, we're going to give a cos. Okay, also for k equals 0, zk is just 1. So k equals 0, lambda 0 is equal to 0. And that gives me the stationary state. Because the k equals 0 mode, this term here will be 0 times time, so it won't decay away with time. The other ones will have negative real parts, and so the other modes decay with time. So let's just see what happens for k very much less than L. Then I can expand this, right? Expand the exponentials. K is very much less than L. I can expand up to second order. I'm sorry? Yellow chalk, yes. So for k very much less than L, I can expand this, and what I get is lambda k. So the first term from each z will be 1, which will cancel. Then I'm going to have 2 plus I k over L, p minus q, then minus p plus q, 2 pi squared k squared over L squared, plus the higher order terms. But from this you see that, so this is an imaginary part, so it will give some oscillations, and the oscillations have period so this will lead to oscillations with period L over P minus Q. And this part is real, and it's less than 0 for K greater than 0. So this will lead to a decay, and this gives oscillations. The period of oscillation is just simply the time it takes the particle to go round the ring. So again, the fact that there's a current, we don't have detail bounds, there's a current, we see that quite naturally we're going to get oscillations in the decay of the probabilities to the stationary state. So what I'm saying is if it starts from somewhere, it will go round, and you'll see that in the probability distribution until you wait a very long time, and you reach the stationary state, and it forgets about its initial condition. So the important thing is that this is real, and the time it takes to relax is, let's call it tau, or tau k, and we'll define it as 1 over the real part, or the magnitude of the real part of lambda k. And what we see, so this is the real part here, 1 over the magnitude of the real part goes like L squared, plus some, multiplied by some other stuff, but basically it's L squared. And that's important because we define this as L to the Z. This is a little z. And here, the dynamic, excuse me, let me go up here. So the dynamic exponent, I'll denote by z, is equal to 2. And this is common to diffusive processes. So here was a random walker. It had some, generally a bias, but it's a diffusive process. And then this exponent z, which measures the time it takes to reach the stationary state on a system size L, is 2. So it takes time L squared to reach the stationary state. And we see it clearly from this eigenmode decomposition. So the important things, just a summary, the dynamic exponent is 2, but generally we have oscillations. And generally these eigenvalues are complex when we're in a non-equilibrium situation. Okay. Let me now, in the time that remains, okay, hopefully that was a useful example. I just wanted to stress the dynamical exponent is going to be important. And just intuitively, one often says it's the time for the constituents to realize that they're on a finite system of size L. You have to be a little bit careful. That's a very loose description. Here you see the particle was actually going round and round with some finite velocity. So it kind of explored the whole system in a time shorter than L squared. But to reach the stationary state, it takes time of order L squared. Okay, so it's important to get used to thinking in terms of relaxation times and dynamic exponent. Right, so that was a particular example. What I want to do now is let's look at the general theory. So if I go back to expression 2b, remember this was the master equation, and I just wrote the probabilities as a column vector, which I wrote as a ket vector, but don't let that worry you. It's just as a way of writing a column vector. So remember 2b was dp by dt. I'll drop the time dependence is equal to mp. Oh, okay, maybe I should keep it in. So the formal solution to this although this is a matrix, it's exactly the same as a first-order differential equation. So the formal solution is, in fact, P of t, this ket vector, is e to the m times time p 0. So if you, for those of you who haven't seen that kind of thing before, sort of writing an exponential of a matrix, it seems, at first that seems a very unnatural thing to do. The way to think about it, just think about it as a power series. So the way to check is you write the e to the mt as a power series. So this is just 1 plus mt plus m squared t squared over 2, etc. And then you can check that if I take the time derivative, I get m times 1, m times t. Have I done something wrong? No, I think I'm okay. I know, if I take the time derivative, I get m. Then I get m squared times t, and so on. So it's clearly I get m times the original expression. So it works. So you think, hooray, you've solved it. But again, it's a formal solution, so it's not too much use when you actually want to write down an expression. But formally, that's the solution. And one thing to note that I tried to stress is that m in general is not Hermitian. So in quantum mechanics, you probably are used to Hermitian matrices or Hermitian operators, and then you have nice real eigenvalues, and you know that your thing is diagonalizable. Here generally you have complex eigenvalues. So what this implies is that you have complex eigenvalues. And also the other thing is that you have distinct left, right eigenvectors. So what I mean by that, I can write an eigenvector on the right. Let me label it by lambda, the eigenvalue. Yes. That's right. I don't. Yeah, I'm going to assume it's diagonalizable. Yes, it will be a normal, right. It will be, right. I'm going to assume it, this is a technical point, but it's a very valid point. I will assume it's diagonalizable. In general, no, it's actually, you can reduce it to Jordan normal form. And you may have some blocks that you can't diagonalize, but that's a minor point. Okay, it's easier to assume it's diagonalizable, then we can see what happens. No. No. Okay, so I'm just going to assume it's diagonalizable. That doesn't impose any stringent constraints. Okay, and then the left eigenvector. Right. So then you might be a bit concerned we've got distinct right and left eigenvalues, but you retain an orthogonality property, which is nice. And what we have, so usually in quantum mechanics you have orthogonality, right? If you have a Hermitian matrix, you have orthogonality of the eigenvectors. Here you have something called bi-orthogonality. And what this means is that if I take the scalar product, so here I'm using Brown-Ket notation, and this is meant to be scalar product of phi mu and no, got it wrong way around. Psi lambda phi mu is actually, if I normalize things correctly, I get delta mu lambda. So the right eigenvectors are orthogonal with the left. That's the way it works. And also if I assume, this comes back to the point Repito was making, if I assume diagonalizable so generally, it's not quite diagonalizable, but you can put it in normal form, and the things are just a little bit more complicated. So it's a harmless assumption, I hope, that I'm saying it's diagonalizable. Then I can write a complete set of states. So I write identity is the sum over lambda, phi lambda, mu lambda. So hopefully, this you're familiar with from quantum mechanics, this complete set of states. And also I saw it last week. Kedar was using this quite a lot. Okay, so then if we've got that, then we're in business. So this expression here, I can insert a complete set of states. Right, so again, e to the mt acting on this eigenvector. Again, if I just take it slowly, if I expand in this way, and it's acting on an eigenvector, so that each m will just become lambda. So I'll have 1 plus lambda t plus lambda squared t squared acting on the eigenvector, which is just e to the lambda t. So just go through, convince yourself that you're happy with that. Because this is an eigenvector, then this just becomes sum over lambda e to the lambda t. And phi lambda. And then I have some coefficient. Excuse me, I made a mistake. That should have been psi. Psi lambda p is 0. So what I see is that the stationary state at time t, it's a sum over these eigenmodes, and I've got this e to the lambda t, which is exactly what I saw for the random walk. And this is just some coefficient that comes from the initial conditions, which I can compute. But the structure is just the same as the random walk. I've got these eigen modes here, these eigenvectors of m, and then it's got an e to the lambda t. So if I want to compare with, so CF means compare with the random walk problem. So for the random walk, our P of JT, in fact, becomes, right, so remember, I'm writing, the ket P is just writing all the probabilities in a column vector. So P of JT is just the jth component of that column vector. So it actually is like this. Okay, that's just notationally how one writes that particular probability. It's the jth component of the column vector. And so that's going to be, in this language, sum over lambda, e to the lambda t, j phi lambda, and then psi lambda e 0. And so if I compare with what I had over here, then you see that I've got the e to the lambda t here. I've labeled the lambdas. Then one of those factors will be e to the 2 pi I k L over minus j, and the second one will be this exponential with j naught. But here, Okay, I choose a particular normalization, so I have to just change where the L's are. But if I compare with the random walk, then in fact, J phi lambda k is 1 over L to the half e to the minus 2 pi I k. Yeah, J over L. And psi lambda k J 1 over L to the half e to the 2 to the plus 2 pi I k J over L. And you can check the orthonormality, which is basically what we did for the orthogonality of the discrete Fourier transform. Okay, so after all that, the point was, this is the general theory, that generally you're going to have some eigenmode expansion. And what I've tried to show you is that, yeah, this corresponds in the one particle case, the eigenmodes are just the Fourier modes, which is very nice. The bad news is that that's not going to work when you have an interacting system. It's not as simple as that. But for this one particle system, it is that simple. Okay, so let's go back now and look at the general properties of, so this is the general solution. We've got a sum over lambda of this. So then, generally, we have one eigenvalue, lambda equals 0. And this gives the stationary state. And if our system is ergodic, by which I mean if we can go from one configuration to any other through some sequence of transitions, then this eigenvalue is non-degenerate, and there's a unique stationary state. So ST is my abbreviation for stationary state. Now the other eigenvalues, we have lambda, the real part of lambda is less than 0. So the other eigenmodes will decay away, and we'll be left with the stationary state at the end. And the time to relax to the stationary state we'll call tau, and it will be given by 1 over the magnitude of the real part of the second largest eigenvalue. The largest eigenvalue is 0, so we're interested in the second largest one. And the difference between the two, basically, well, we know that lambda 0 is 0, so that's the real part of the second largest eigenvalue. That gives the relaxation time. And this is known colloquially as the gap. And, okay, so that's what we want to calculate. Generally, we want to calculate the 0 eigenvalue, and the associated eigenvector gives the stationary state. The dynamical properties, the long time relaxation is given by the gap. So that's what we really want to know about the spectrum of eigenvalues. Okay, I'll leave it there. Are there any questions? Yes. I'm sorry? Yes, so symmetric, there's no oscillation. Yes, okay, so basically Yeah, right. For P equals Q, this term disappears. Right, so P equals Q, this term disappears, but you still have this one. So the relaxation time will still be L squared. Yes, yes, I know. But what I'm saying, that comment came from the existence of this term. So if P doesn't equal Q, you have this term, which gives a period of this. So your question is, what happens when P goes to Q? Well, this period diverges. So there's no oscillation. Yes, I mean the period is of order L. No, it's just not, it will visit all the sides, but it's this term that's the important one for the relaxation. Yes, yes. So that's why I'm sorry, I didn't mean to confuse you. When you have, right, this is the important term for the relaxation. What I was saying is that often, right, one says loosely that the relaxation time is the time to explore the whole system. And it's actually, that's not quite true. That's what I was trying to say. So I agree with what you're saying. It doesn't, this term shows that the particle will go round and round. So actually it will visit the whole system. It just hasn't relaxed yet. And also, yes, there's a funny thing here. When P goes to Q, this time actually diverges. So it's of no interest. Yeah, sorry, forget that. That kind of overcomplicates things. This term is the important one for the relaxation time. Yes. No, you can have, the other ones can be, you can have degeneracies, yes. Which is, yeah,